In this problem, we're given a function f of x equals x e to the x, and we're asked to determine where the function is concave down and to find any inflection points. Both of these pieces of information, concavity and inflection, are described by the second derivative of the function. Where the second derivative changes sign will be the location of inflection points, and the places where the second derivative is negative will be places where the function is concave down. So in this particular problem, the approach is going to be to find the second derivative of the function and create a sign distribution. All right, that's the approach. So first things first, we'll find the first derivative. The first derivative of this function, I'm going to view this as a product rule between x and e to the x. So I want the derivative of the first times the second plus the first times the derivative of the second. Derivative of the first is just 1, leaving the exponential alone. Then we leave the x alone, and the derivative of e to the x is e to the x. So that was a product rule. And I'll just clean this up a little bit. I've got an e to the x and an x e to the x as my first derivative. Now we could take and factor out the exponential here if we wanted to, and then do a product rule for the second derivative, or we can leave it the way it sits and clean up afterwards. And I don't really see an advantage of one over the other. In fact, there's one little shortcut here. The derivative of e to the x is simply e to the x, and the derivative of x e to the x is a product rule. And in fact, it's the same product rule we had before. So this product rule right here is going to lead to the same two terms that we had before. So it should be e to the x and x e to the x. So kind of interesting when that sort of thing works out. It's fairly rare, but it worked. And now I will factor out the e to the x from these three. If I do that, I'll be left with a 1 plus 1 plus x, which is simply 2 plus x. The only interesting x value here is the number -2. And now we just check to see what the signs on the second derivative are near here. One word of caution here. If we were just looking for inflection points, it'd be very tempting at this point to say that we know there's an inflection point at -2, but in fact we don't yet know that. We need to see the sign change here, and I think in this problem it will. But in general, if you're asked for inflection points, be sure to check. If the signs do not change, you can have positive, 0, positive, for example. That would imply that you do not have an inflection point. It means there's a very flat spot in the function. So let's walk down the number line. If we pick a number out here on the left side of -2, the exponential will be positive, but the 2 plus x will be negative. So in this region we're going to have a positive times a negative, and so the result will be negative, which means out in here we are concave down. That shape, or some part of it. And to the right side of -2, if x is larger than -2, then x plus 2 will be positive, and again the exponential is always positive, so out in here it's a positive times a positive, which is positive. So out in this region we're concave up, or some part of it, and I can now say there's an inflection point. The inflection point, again, is a point on the graph, so we should list both its x-coordinates and its y-coordinates. The x-coordinate's -2, and the y-coordinate then would be -2 e to the -2. I'm just plugging in. And if you want a decimal representation of that, you can ask your calculator. So we do have an inflection point at -2,